Right, so what we're going to do is I'm going to start off about 45 minutes. I'm going to run through this really quickly. I'm not going to ask you questions, I'll do all the talking. So as far as tonight's concerned, we're doing Unit 3. So Unit 3 consists of half a dozen of the basics: numbers, fractions, decimals, percentages, ratios, algebraic manipulation, coordinates, and application of linear graphs. Call them the basics because they're all 3 units. The advantage of this unit is you can use your calculator to do those. But don't get me wrong, there is definitely a ratios question in what you're doing in your exams and tonight's paper. There is a coordinates question in there. So you can't just forget about them. You've got to keep going over those basics. And the basics are the difference between getting around the pass mark and falling 10 marks short. Okay, to get 20 marks above, that's when you get good at the rest of the stuff. Okay. So what we're going to concentrate on tonight are the rest of the things on this list: angles, properties of polygons and circles, drawing construction, 2D representation of 3D shapes, perimeter, area and volume, Pythagoras, the rest of them. Some of them are core to Unit 3. They will appear in every Unit 3 exam. Angles does, properties of polygons does, drawing and construction doesn't, 2D representation of 3D shapes doesn't, perimeter, area and volume will definitely be in there, Pythagoras will definitely be in there. Measures, definitely. Reflection and rotation, yes. Trial and improvement, no, but it might be tonight. Bearings, maybe, maybe not. And quadratic graphs, a lot of the time not, but occasionally it does appear. So they're not evenly weighted. Some of them are definitely, they want to test your perimeter, area and volume skills. They have to, because it's one of the basics in functional skills as well. Okay. So I'm not going to cover these because these are covered under Unit 2 and you should all be on top of your basics by now. But don't get me wrong, there'll be at least 2 or 3 questions on these topics in tonight's paper and the paper you take in June. So let's go back to the start then as far as Unit 3 is concerned. Types of angles. You need to be able to estimate and measure angles. You need to recognise them as well. So you need to be able to spot an acute, obtuse, a straight angle, a reflex angle, and a right angle. And they like these as starters because they're nice, easy questions to settle your nerves. Estimating angles, have an idea of an angle, so if you have to measure an angle, that you're measuring the correct thing. So here it's about 45 degrees. Here it's got to be more than 90, it's about 110. So try and get this whole angles bearings thing in your head to check your answers if you do have to measure them. Angles at a point then, so when all these lines meet at a point, the angles around a point equal 360 degrees. And they might give you one of these where 1 or 2 of those angles are missing, but you have enough information to solve them. Okay. When 2 straight lines cross, it starts throwing up some rules with angles. The angles opposite are equal. And again, they might give you a missing angle or some information that allows you to solve it. Here you could just be given one of these angles, like that's 100 degrees. And it's quite easy to solve because that must be 100, in which case I've got 200 there. I know there's 360 around a circle because it's angles around a point. Okay, that leaves 160 split between 2, which means these must be 80 each. Okay, and that also leads to the straight line rule where this and this add up to 180. So there's lots and lots of ways of solving these things. Angles on a line, when they cut exactly at right angles, posh word called perpendicular. Sometimes they might not use the word right angle. They might say this line is perpendicular to that one, or draw a line that is perpendicular to this. Okay, perpendicular just means at a right angle. Parallel lines are lines that never meet. The distance between them is always the same, and they're annotated in maths with these little arrows. Okay, and they're quite important because when you throw another line across them called the transversal, it throws up a set of rules. Okay. And there are some basic rules you need to know. This is the alternate angle, and an alternate angle is this angle here is the same as that angle there on your transversal when it cuts a parallel line. Okay. The next one you need to know is corresponding angles. So B corresponds with B. They're the same angle, and visually you can see that. You can see this is obtuse, that's obtuse. These correspond. So corresponding angles are on the same side of your transversal. And then we've also got the interior angle, which is sometimes called the allied angle. And the 2 angles that are trapped inside your parallel lines add up to 180 degrees. They have to, because if you go back to one of the earlier rules, this is an alternate of that, and D and E are on a straight line. Okay, so you can see how all these angles can be derived by knowing straight line rules, rules around a circle, and so on. Okay. Angles also appear in shapes, and everybody knows it's 180 degrees within a triangle. But the fact that the angles can be the same or different in a triangle actually defines a triangle. So triangles aren't defined just by the length of their sides, they're also defined by the length, by each of the angles. So a scalene triangle, a lot of people say, oh, all of the sides are different lengths. Yes, but all of the angles are different. They have to be. Okay? An isosceles triangle has two angles the same, which also means they've got two sides the same length. Equilateral, they're all the same, and the angle has to be 60 degrees, because it's 180 divided by 3 equal lots. Okay? And a right angle has to have a right angle in it somewhere. Okay? These sides might not be the same length, or they might be. Pythagoras will tell us whether they are or they're not. So we've got some general rules when it comes to angles inside and outside shapes. The rule for the angle inside the shape is the number of sides. So this is a pentagon that has 5 sides. So I've got 5 sides, I take away 2, and I multiply it by 180, and it tells me the total of the interior angles. So 5 take away 2, let's do it. 5 take away 2 is 3, times 180 gives me 540 degrees for the total of my angles. There are 5 angles inside there, so I divide by 5, and it tells me that the interior angle of a pentagon is 108 degrees. Okay? So we can use that formula to work out the interior angle of a shape. And that rule about angles applies to not just regular shapes like the pentagon, but something as basic as a square. Everyone knows a square has 360 degrees in it because it's got 4 lots of 90. But there are 360 degrees in a trapezium or a parallelogram. Okay? So the fact that it's got different angles doesn't mean that they don't all add up to the total within that shape. Okay? We then talked about lines of symmetry, and a line of symmetry is like a mirror line where you can put it down the centre of the shape, and what you have on one side of the line is the same on the other. Okay? So you might be asked about lines of symmetry. Very, very rarely, if ever, you'll be asked about a plane of symmetry, but it's on the curriculum. And a plane of symmetry is like a line of symmetry, but because the object is in 3 dimensions, you have to think of a piece of paper that cuts through something. So it's like a sandwich. Here I can cut it this way, in half that way. I can cut it down the centre of that line, or I can cut it down the centre that way. So the only one they'll really ask you about a plane of symmetry is a cuboid, and it has 3 planes of symmetry. Then they might ask you about rotational symmetry. Okay? And rotational symmetry is putting a pin in the centre of whatever shape they give you and spinning it round and seeing how many times it maps onto itself. So how many times does that yellow dot map onto the same shape? And as you go around, you can see that particular object has an order of 4 for rotational symmetry. Now to shapes. Shapes called polygons. Poly meaning lots of, and gon is a side or angles. So polygons fit into 2 main flavours, either regular or irregular, and that's really important, okay? Because regular ones have all the sides the same length. So a regular polygon is an equilateral triangle or a square, or this one, which should be over there as well, a regular hexagon. Irregular shapes have different length sides. So it could be a trapezium, a rectangle, a scalene triangle, or an isosceles triangle, because some of the sides are different. And this difference is really quite important, because when you're naming these shapes, triangles, pentagons, hexagons, octagons, you should really use a prefix. Regular means all the sides are the same, but conversely, irregular means it could be this. This has got 6 sides, but they're all over the place. So it's an irregular hexagon. Got that? Okay. Right. So, down to shape recognition then. You've got to be able to recognise these shapes. Squares, rectangles, all the types of triangles that we've just covered. A rhombus, which is one of their favourites, we'll come on in a minute. A parallelogram, trapezium, kite, and then pentagons, hexagons, octagons, and decagons. So what's up there? you should be able to identify straight away. Okay. Now, we were talking about the interior angle of all these shapes. There is also a trick to work out the exterior angle of a shape really easily. Okay, so the interior angle we talked about for the pentagon. But if you take the side of the pentagon and extend the side lengthwise, so you've got a straight line, if we know that this is 108 from what we did earlier, then this external angle must be 72 because they're on a straight line. So that 72 degrees represents the external angle of a shape. Now, there's a really neat trick to work out the external angle of a regular shape. In this case, we've got a pentagon which has 5 sides. And if I divide 360 degrees by the number of sides, it tells me that the external angle is 72. So we have a method of working out the interior angle, and we've also got a method for working out the exterior angle. Okay. Good. Quadrilaterals. Quadrilaterals are 4-sided shapes. Okay? And they can be squares, rectangles, trapezium, kite, parallelogram, rhombus. No such thing as the D word in there anywhere. It's a rhombus on its end. Okay? The rhombus is special because it has a lot of properties that a square has when they ask you to do this. And this is the diagonal properties of a quadrilateral. What they might ask you to do is connect the opposite corners on a quadrilateral and talk about what that does with respect to the angle here and the centre in here. Okay? It's quite a complicated thing, but this for the square, if we look at the square and we draw our diagonals, this right angle is cut exactly in half into 2 lots of 45 degrees. So the diagonal bisects the angle. Also, the lines where they cross are, there's the P word, perpendicular as well. Okay? So to help you, I gave you the handout, lovely expensive colour handout, on the properties of the quadrilaterals. Okay, so we've just talked about the square. You can see from a kite that where the 2 diagonals cut, you have a right angle. But it doesn't cut this angle here exactly in half. So it throws up different properties. And the reason they love the rhombus is because it has a lot of diagonal properties that the square has. In other words, where they cross-cut, it's 90 degrees, and it cuts the angle exactly in half. Okay? And that's why they like the rhombus, because the diagonal properties for the square are similar to the same as the rhombus. Tessellation. Tessellation is tiling. So we've got our shapes now and we're sticking them together. So here we've got a hexagon and they fit together. Here we've got squares with equilateral triangles. They all fit together. And the reason they fit together is 360. They create 360 degrees when they're put together. One shape that you know doesn't tessellate, and that is the pentagon. And the pentagon doesn't tessellate because the interior angle is 108 degrees, and 108 doesn't go into 360 very well at all. Okay? However, all of the other shapes tend to go into 360. You need to be able to recognise 3-dimensional shapes. You have to recognise cubes and cuboids, cylinders, triangular prisms, square-based pyramids, triangular-based pyramids, spheres, and cones. Okay? Circles. You need to know the terminology for circles. And quite a lot, every other exam paper has one of these diagrams with some of the labels covered up for you to label. Okay? So the diameter goes from side to side through the middle. The radius goes from the middle to the outside, and the circumference is the red that goes around the outside. A lot of people know those because they're the basics of circles. The ones they try and catch you out on are these. A tangent is a line that just touches a circle. A chord goes from one side of the circle to the other, but not through the centre. And the area that the chord cuts off is a segment. A sector is like a piece of pie where it touches the edge of the circle from the centre. And an arc is the outside of the circle that relates to the sector. Okay? So there's some labels there that they might get you to do. In order to calculate things with circles, you have to know these 2 equations off the top of your head. The circumference, the distance around the outside of the circle, is pi times the diameter. It's basic algebra. Sometimes they'll give you the diameter and you multiply pi by the diameter to get the circumference. Other times they might give you the circumference and ask you for the diameter, and it involves a bit of algebra. If you know this, but you don't know that, and you need to get it on your own, you divide this by pi. Okay, hint over. Area is pi r squared. Okay, they will try and muddle you up between diameters and radii. So always make sure the diameter is the distance from edge to edge through the centre. The radius is from the centre to the edge. The radius is half the diameter. In your calculations tonight on the big day, pi is equal to 3.14. End of. Don't use it on your calculator, 3.14159267787, whatever it goes on forever. Just use this, and it'll keep things nicely rounded for you. Okay? And that's what they recommend you do on the front of the Unit 3 paper. Constructing triangles now. If they want you to construct a triangle, they'll give you some clues, and those clues come in various shapes and sizes. The side angle side clue means they'll give you a length of a side, tell you that the angle is 30 degrees, and tell you that the other side is another few centimetres. That only leaves you to fill in the missing gap to complete your side angle side triangle. So they'll give you two sides and an angle. Angle side angle means they'll give you a side and they'll tell you an angle of 30 and an angle of 40, and you just draw lines out to infinity, and where they cross, that's your triangle. Okay? Side, side, side is one of their favourites. They'll give you a length of 4, they'll give you a length of 5, and they'll give you a length of, I don't know, 3. Okay? That's easy to draw with a compass. Get your compass out, you set 4 in your compass, and then you set 5 and draw an arc. Ooh, draw an arc, and then set 3 on your compass and draw an arc. Okay? So the side, side, side one is all about drawing with a compass. They love the equilateral triangle because you use the side, side, side method for it. So if you wanted to draw an angle of 60 degrees, because an equilateral triangle has 60 degrees, so when you hear 60 degrees, alarm bells go, think equilateral triangle. To draw it, just create a side, any length you like, 5. Get your compass and set your compass to 5 and draw an arc there and an arc there. And where they cut, you will draw the perfect equilateral triangle and the perfect 60-degree angle. Okay? And that's why they like equilateral triangles so much, because it's another way of asking for it is this 60 degrees. Construction now and bisectors. To bisect a line, which is exactly the same as bisecting 2 points, Aberdeen and Birmingham, and I want to put a line between them, you get your compass and you set it to over halfway. Put your pointy end there and draw your arcs top and bottom. Swap your pointy end the other way and draw your arcs top and bottom, and where they cross, you cut that line exactly in half. Or you cut these 2 points exactly in half. A line is just joining 2 points, okay? So if you wanted to build a supermarket closer to Aberdeen than Birmingham, you'd draw it to the left of that line. An angle bisector is I want to cut this exactly in half. So you put your compass to any length and set it and leave it at that length. You make a nick there and there on the 2 sides, and keeping the same length, you draw an arc in the centre, and where they cross, that perfectly cuts your angle in half. Not only does it cut this angle perfectly in half, it also puts a line exactly the same distance from that line as that line, which was in your homework the other night. Okay? So as far as loci are concerned, what we've just done, equidistant from 2 given lines, equidistant from 2 given points, is this. So loci 3 and 4 is bisecting a line, bisecting an angle. Okay? A fixed distance from a given point on loci is I've got a point and I want to draw end up drawing a circle that is 10 centimetres away. Because a circle, every point on that circle is 10 centimetres from that point. So a loci from a fixed point is a circle. The only tricky one is 2, and that is a fixed distance from a given line. So if you see the loci for a line, it will look like a racetrack. Okay? So you've got your line here. In order to draw this, you have to draw parallel lines above and below at the set distance. Let's make up a distance of, say, 2 centimetres from there to there. So you draw your 2 parallel lines 2 centimetres above and below the line. Then, to stay 2 centimetres away from the end, which is essentially a point, the distance from a point is a circle, so you draw a half circle at 2 centimetres at either end with your compass. And it's the racetrack. So if you get the loci of a point for a line, it's a racetrack. I'm going to talk about congruence. Congruence is where it's the same image as the object, but in a different place. So if our object is the green triangle and our images are orange, red and blue, the object has been translated to the orange, so we just slid it across. It's been reflected to create the red one, and it's been rotated to create the blue one. So reflection, rotation and translation are all congruent processes. Similar shapes are a scale factor. So enlargement is a similar object. So it's the same shape but a different size. Okay? Are you happy with congruence and similarity? Okay, good. Pythagoras. Pythagoras is a guy who came up with this idea for right angled triangles that said, if I've got a side here, a small side and a small side, if I make squares out of those sides and add them together, it's equal to the long side. And that long side is always opposite my right angle, and it's called the hypotenuse. So he said, in mathematics terms, if I square this length here, a squared, and I square that length there, plus b squared, it's the same area as that long length, c squared. That's what Pythagoras is. How do we use that in maths? We use it by saying, here I've got 3 squared, which is 9, plus 4 squared, which is 16, is equal to 25, and that's the same as x squared. So in order to find out what x is, I need to square root 25, which is 5. So x is equal to 5. The numbers on your papers might not be this straightforward because you have calculators. Okay? This is Pythagoras, but where you're missing one of the smaller sides. Okay? So, I know that a squared plus b squared equals c squared, but this time I know what c is, because c is the hypotenuse, and my hypotenuse is my 13. So that's 13 squared. A I don't know, but b is 12 squared. So now you need to solve this using a basic bit of algebra. A squared plus 144 is equal to 169. I'm trying to get a on its own. So the first thing you do is take away the 144 on both sides, and it means that a squared is equal to 25. Again, we have that dilemma with Pythagoras a lot of the time, where you're not just looking at a, you're looking at a squared. So to get a on its own, you need to square root the 25, so a is equal to 5. Everybody happy with that? Good. Perimeters. Perimeter is a distance around the area of a shape. Can be straightforward if it's a square, rectangle or whatever. If it's a complicated shape, pick a start point and go round in a logical manner. Okay? Filling in any missing lengths that they might give you hints and tips for. Okay? Length is obviously in basic units, millimetres, centimetres or metres. An area is defined as the space inside the shape. So to calculate the area of a square or a rectangle, it's the width times the height. To calculate the area of a triangle, which is half a square, you just half the base times the height. Parallelogram is the vertical height times the base. A circle is pi r squared, and if they give you something that looks strange, break it down into its basic shape. So you're dealing with a square and half a circle. Shapes with no numbers. If you get asked to work out the perimeter of a shape that has x's instead of numbers, do exactly what you'd do if you were walking around a perimeter and add the letters. X plus, that's going to be 3x, plus another x that side, plus 3x's. So as I walk around, I've got 1, 4, 5, 8 lots of x. And that's how you deal with letters when they appear in perimeters. Okay? They might then say, this is going to be a field and I've got 40 meters of cable, so what is x going to have to be? And it just becomes 40 equals 8x. I want x on its own, so I just divide by 8 on both sides. And it tells me that x is equal to 5 meters. Okay? And that's how you solve something with perimeters. If they ask you for an area with letters, all they'll get you to do is say, right, what do I do for the area of this with letters? It's the width, which is 3x, times the height, which is x, which gives me 3x squared. And that's about the limit of what they will give you. Okay? They might give you a value to put in there. If they do, it's just substitution, which you did a lot of last week. Volume. The way to deal with volume of any shape, three-dimensional shape, is look at the two-dimensional shape that you know how to work the area out for and multiply it by the depth. So if it's a square or a cuboid, just take the basic shape, the width by the height, and then multiply it by the third dimension, the depth, once you've worked that out. If it's a cylinder, the hard bit is working out the area of the circle, the pi r squared, and then just multiply it by the depth of the cylinder. Same for a prism. If they give you a triangular prism, work out the area of the triangle and then just multiply it by whatever's behind it. Representing 3D shapes. Nets, they like nets. Nets appear on every other paper. Nets for a cube. Basically a net is folding a box out flat, and we know there are 11 nets for a cube. So the sorts of questions they might ask you are, is it or isn't it a net for a cube? Or they might give you a box and say, draw the net. So there's lots of net type questions in papers. Isometric drawings come up once every 3 or 4 years, so you still have to know how to do them, and you've got dotty isometrics and triangular isometrics. There is a right way and a wrong way for the paper, so as long as you keep your exam paper orientated the correct way, you shouldn't have a problem. They will give it you in the correct way. Having to draw it, well, it's not as straightforward as you think, because the triangles, to be 1 centimetre apart, you have to go in those directions. You can't draw a square like that because it's a rectangle. And these dots are 1 centimetre apart on the diagonals, okay? So you draw the top, drop down the sides, and draw the base for an isometric cube. If you were doing it on the triangular paper, it's the same principle. Draw the top, so this is a 2 by 2 by 2, drop it down 2, and then connect the bottom. So there you've got a triangular isometric of a 2 centimetre cube. Okay. Plan and elevation. Plan is looking down on an object. Elevation can be front elevation or side elevation, and they'll get you to draw it with respect to these 1 centimetre cube things. They're quite keen on those. Transformations proper now. We talked about them briefly earlier when we were talking about congruence. Rotation. When you talk about rotation, you need to talk about which direction you're rotating, clockwise, and then what you're rotating it about. 0, 0 is the origin. It's the centre of a grid. Some people didn't realise that. Okay, so when you're talking about the object and the image is always t dashed or a dashed or whatever. Okay, so clockwise or anti-clockwise, and don't forget the expression a turn. So this has been rotated a quarter turn clockwise. Reflection involves a mirror line. The trick of a mirror line is the distance from the mirror line you draw to your opposite point. So here it's a long way away and it ends up flipping it. If they give you one of these and it's on a bit of graph paper, the mirror lines are defined by equations. So if it's the diagonal on a piece of graph paper, it's y equals x. If it's a vertical line, then x equals a number. So x equals 3 is a vertical line through the value of x3. Last week we talked about this. For a y value equals something, it's a horizontal line. So y equals 2 is a horizontal line through the value -2. Okay. Translation is sliding an object across. Yes, you can describe a translation using 4 to the right and 5 down. Okay. Can't say 4 across, because across could be left or right. So if you're going to describe it in words, it's 4 to the right, 3 down. If they ask you for a vector specifically, a vector shows left-right movement an up-down movement. So if it's right, it's positive. If it's left, it's negative. If it's up, it's positive. If it's down, it's negative. So 3 minus 4 means 3 to the right and 4 down. Don't forget about objects and images, and annotate images with a little dash. And all of these are what we call congruent processes. It's the same shape in a different place. Enlargement, which is our similar process, makes things bigger. Everything goes up or down in proportion. In other words, if one side is increased by a scale factor of 2, then the other does. But do remember that things can get smaller. Remember your homework? Something got smaller. It wasn't a scale factor of 2, it was a scale factor of... Okay. So, the hardest one they can ask you on enlargement is where you're given a centre of enlargement. So if you had to enlarge this square by a scale of 2 from that centre of enlargement, you have to do everything relative to here. So if it's 5 along and 2 up to get to this corner here, then you need to go 10 along and 4 up to get to its equivalent corner. Once you've got a reference, you can increase everything on here by 2. So 2 becomes 4, 3 becomes 6, and you can reconstruct your enlargement from that reference. Okay? Conversely, they could give you the enlargement and the original and ask you for a centre of enlargement. And that's quite straightforward. All you need to do is connect the corners in a straight line and extend the line. So you connect this corner to this corner and carry on going. You connect this corner to its equivalent corner and carry on going. And you can do it with a third one, just to be on the safe side, to show you that's how you find a centre of enlargement. Bearings, getting pretty close to where we were the other day. Okay, bearings all may start from north. They must be measured clockwise, so you go clockwise round, and it must have 3 digits. And a lot of the time, they'll tell you and write down the 3-digit bearing of such and such. That doesn't mean it's got to be bigger than 100. They're trying to give you a hint that there's a leading 0. So in your homework, a lot of people, for small bearings of 20 degrees or 40 degrees, were being thrown by the clue that they're giving you 3 digits. All they're saying is it's 045 or 020. Okay? The most important thing about bearings when you're talking about 2 points is from something. Again, in your homework, there was still a lot of mistakes occurring because people weren't working out the bearing from. So here, it's the bearing of B from A. So A becomes a reference. A is the thing with north on that we're going to measure round to B with. Okay? You also need to know the cardinal points, north, south, east and west, and the intercardinals. So they might give you clues on bearings. So if they want words, they'll ask for words. If they want an angle, give them an angle. Give them the accuracy. Okay? They'll only ask for words specifically. This is what they want. They want 105 degrees or 045 degrees. Speed, distance, time. We've got the speed, distance, time triangle. Just remember the distances at the top. You cover up the things that you don't know. So if it's speed that you don't know, you divide the distance by the time. Things to watch out for are units. So beware of decimal times or converting times. Everyone remember that 0.1 of an hour is 6 minutes and that 0.1 of a minute is 6 seconds. Because it has a base of 60, we change over once we get to 60. Okay. Distance tables. These are tables that go diagonally across. The way to read them, if I'm looking for the distance from Leeds to Sheffield, is go down from Leeds, across from Sheffield, and where they meet on the grid, that's the distance. They're really, really, really keen on these linked distances, okay, where they'll tell you A to C is 100 miles, and B to C is 40. What's the missing distance? A to B, and you have to calculate it. There might be a D on there, there might even be an E. Okay? Don't let them throw you, it's just the distances between them. Everyone happy with that? Good. Measurements. The basic measurements for length, weight and volume are meters, grams and litres. They're the base units. Okay? The kilos mean they're the big things. They're 1,000 times bigger than this. So kilometre, kilogram, okay? If they're smaller, it's centi and milli. Centi is 100th and milli is 1,000th, so centimetre, milligram, millilitre and so on. So make sure you get the right scales if you're converting between these units. For example, they might get you to calculate the volume of 10 glasses of water at 500 millilitres each, so it's 5,000 millilitres, but then they'll ask you for the answer in litres, so it becomes 5 litres because it's 1,000 per one. So don't get thrown, and there's always a conversion in Unit 3, very similar to the one that I've just done. Okay. Conversions between imperial and metric units, you need to remember these four, because if they appear in the exam, they're not going to give it to you for nothing. You have to remember that 5 miles is 8 kilometres, 4.5 litres is a gallon, 2.2 pounds is a kilogram, and 1 inch is 2.5 centimetres. You also have to remember, and they're not going to give you this, that there's 12 inches in a foot. And that's an imperial to imperial. But they expect everybody to know that. Some people don't. Compound measures is where you mix the units, miles per hour, kilometres per hour, and metres per second. In your homework, there was a thing with the old speed limit and the guy who did 600 metres in 27 seconds. Make sure you're talking in the same units, okay? Metres per second. Convert everything into the same units when you're doing the comparison. Wow, up to last week. Quadratic graphs has to have an x squared in it, okay? If it's got a minus x squared, it draws a grimace, okay, a frown. So if x squared is positive, it draws a U shape, and if it's a negative x squared, it will draw the other way around. Generally what they'll do is they'll give you 3 things to do on a quadratic graph. You have to do some substitution into the equation and complete a table. So there'll be some gaps in a table. Once you've got the table complete, they'll ask you to plot your quadratic graph on coordinates. When you draw it, you've got to use a smooth curve, and then they'll give you something right at the end that says, when y equals 6, what is the solution for x? And all you do, we talked about it a minute ago, when y equals a value, it's a horizontal line, so y equals 6. Where it cuts your parabola, which is the posh word for the curve, that is where the solution lies to that equation. So x squared equals 6 is solved when x is minus 2.5 and x is 2.5. Okay, and we did that last week. If they give you something complicated like this, again you'll have a partially filled in table, or they'll break it down into individual terms on a bigger table. But all they'll get you to do is complete a table, plot some points, and draw the smooth curve. And then they might add in, when y is equal to minus 6, what's the solution? So go to there, and it tells you how to solve it. Okay. Trial and improvement. Trial and improvement is where you take a stab at a solution to a question. So I've got x cubed plus 9x equals 40. I put 2 in, 26 comes out. I put 3 in, I get 54 out. And then through trial and improvement, trying different numbers, 1 decimal place at a time, you trap it between 2 1 decimal place numbers. So here it's too big at 2.6 and it's too small for 2.5. So I know my answer lies between 2.5 and 2.6. I then put the halfway point between those two in, and in this case 2.55 is too small, so the answer must be bigger than 2.55, which means 2.6 is the closest answer to 1 decimal place. Don't get thrown by this. You can actually do trial and improvement using big whole numbers. So they could say, for example, what's the square root of 2000? And you can just take a stab at 12, and put it in and try 25, and do it to 1 decimal place by trial and improvement. So trap it between 2 whole numbers and then do this process to get it to 1 decimal place. Okay? And that's it. They are all the topics from Unit 3.